Hello, and welcome to this brief presentation on complex numbers. Here we're looking at proving trigonometric identities using deMoivre's theorem. This presentation does assume you've seen previous presentations relating to Pascal's triangle and also trigonometric identities, as these techniques underpin the solutions we're about to review. Within this presentation, we're going to test for correctness of a trigonometric identity using deMoivre's theorem. The proofs undertaken within this presentation will make use of Pascal's triangle, of Pythagorean trigonometric identities, and deMoivre's theorem. There are separate presentations on each of these topics to view should you want more background information. Below is the expression we're going to use. In square brackets here we have r multiplied by cos theta plus j sine theta. It's all raised to the power of n. Using deMoivre's theorem, that's written as r to the power of n multiplied by, in brackets, cos of n multiplied by theta plus j sine n multiplied by theta. This will be the starting point of each of the examples we're going to review on the following slides. Table 1 shows us a recap of Pascal's triangle. Within this table we've expanded the a plus x binomial expansion to the power n up to 8 in this particular case. So a plus x squared, for example, which is a plus x multiplied by a plus x. The expansion is given a squared plus 2ax plus x to the power 2. A plus x to the power 3 is shown as expansion of a cubed plus 3 multiplied by a squared multiplied by x plus 3 multiplied by a multiplied by x squared plus x to the power of 3. Notice with the binomial expansions how the powers of a decrease from left to right and the powers of x increase from left to right. For example, looking at the powers of a, we've got a to the 4, a to the 3, a to the 2, a to the 1. This would be a to the 0. And looking at the powers of x, we've got basically x to the 0 here, x to the 1 here, x to the 2, x to the 3, x to the 4. And that pattern is repeated throughout. We will also be referring to what's termed the coefficients, so taking the expansion a plus x to the power of 4, the coefficients would be 1 here, that's 4 for the next term, 6 for the next term, 4 for the next term, and 1 for the final term. Notice if we've got a power of 4 expansion, we have 5 terms, the power of 5 expansion, we have 6 terms, and so it goes on. Table 2 here shows Pascal's triangle coefficients only between n is equal to 0, n is equal to 8. So purely the coefficients from the previous slide are shown here. So reviewing the a plus x to the power 4, for example, we've got the coefficients of 1, 4, 6, 4 and 1. So just showing the coefficients there with no a or x terms. We will also be referring to trigonometric identities in some of the questions, and the two Pythagorean identities we're going to use are sine squared theta, which can be written as 1 minus cos squared theta, and cos squared theta is equal to 1 minus sine squared theta. They both come from the trigonometric identity sine squared theta plus cos squared theta equals to 1, but I've just rearranged them there for your convenience. Again, for your reference, if you want further information on Pascal's triangle or trigonometric identities, please refer to separate presentations. Okay, within this brief presentation we're going to look at 2 examples, and then I'll leave you with some exercises to attempt. Example 1a is in part A. We're asked to apply deMoivre's theorem to write cos 3 theta in terms of sine theta and cos theta functions. In part B of example 1, we're asked to use the result from part A, and making use of the trigonometric identity sine squared theta is equal to 1 minus cos squared theta. We're asked to determine the identity sine theta multiplied by cos 3 theta as a function of theta. And we're going to use deMoivre's theorem as stated on our initial slide. So we've got the r multiplied by cos theta plus j sine theta all raised to the power n. So we know that can be written as, in deMoivre's theorem, r to the power of n open bracket cos of n multiplied by theta plus j sine n multiplied by theta. So part A, we're given in the question cos 3 theta. We need to initially note that n in this case is 3 and r is 1. R will be 1 in all the examples and exercises we are going to look at in this presentation, but the n value will vary depending on the question. So in this case, n is equal to 3. We've got cos of 3 theta. So step 1. From the above expression, I just reversed the equation. So on the left-hand side, I've got r to the power n multiplied by, in brackets, cos of n theta plus j sine of n theta. And on the right-hand side, I've got my r, and in brackets, cos theta plus j sine theta. And it's all raised to the power of n. Now in this case, we know that the r is equal to 1 and the n is equal to 3. So all I'm doing now is placing in the values of r and n on both sides of the equation. On the left hand side then, because I'm expanding by 1 cube, don't forget 1 cube is 1, so expanding on the left hand side, I'll get cos 3 theta plus j sine 3 theta on the left hand side, and on the right hand side I'll simply get cos theta plus j sine theta, all raised to the power of 3. Now what we do with these type of questions is we equate either the real or the imaginary part depending on which part of the function we are trying to find. Now the question wants us to find cos 3 theta in this case. On the left hand side, the cos 3 theta is associated with the real part of the complex number. The sine 3 theta term is associated with the j part, so that's the imaginary part. So because we're asked to find the expansion for cos 3 theta, I'm only going to equate in step 2 the real parts. So on the left hand side, I simply write cos 3 theta for the real part. On the right hand side, what I'm going to do in a moment is expand the function cos theta plus j sine theta raised to the power of 3. And we'll do this on the following slide. Example 1a continued. Don't forget we're trying to expand cos theta plus j sine theta all to the power of 3. So step 3, I'm going to expand the right hand side of the equation on the previous slide using Pascal's triangle. So I'm going to look for the expansion of a plus x to the power of 3. So I've just repeated part of table 1 here for convenience, and here's the expansion a plus x to the power of 3 and given for us. Now notice in this particular case, a would be the cos theta term and the x would be the sine theta term. So when we expand a plus x to the power of 3 generically, we would get a cubed plus 3 times a squared times x plus 3 times a times x squared plus x to the power of 3. That's the expansion we're given in table 1. So if we apply that now to the cos 3 theta expansion, where we've got cos theta plus j sine theta to the power of 3, then our a term, the first term, is cos theta, so that's cos cube theta following our pattern, that's the a cubed term. The second term in the generic expansion is 3 multiplied by a squared multiplied by x. So in this case that will be 3 multiplied by the a term, which is the cos theta term squared, multiplied by the x term, which in our case is the j sine theta term. Looking at the third term in our binomial expansion, we get 3ax squared. So that will be 3 as a coefficient, the a is cos theta, and the x squared now will be j sine theta all squared. And finally, looking at the last term, which would be x cubed. In our generic expansion, x in our case is the j sine theta term, so that will be plus j sine theta all cubed. So there's our binomial expansion of cos theta plus j sine theta to the power of 3 using our Pascal's triangle table. All I'm doing on the next line is trying to simplify, so I get cos cube theta plus, I just put the j to the front here, so j multiplied by the 3 cos squared theta sine theta, plus here we get 3 cos theta. Now be careful, we've got j sine theta squared, so that's j sine theta multiplied by j sine theta, so that would be j squared sine squared theta. And finally we get the j sine theta all cubed, so that will be j cubed multiplied by sine cubed theta. All I've done on the next line is to replace the j squared term here with -1. If you remember previous work, j is defined as the square root of -1, so j squared is -1, a real number. And also from our powers of j work, j cubed is actually -j. So j multiplied by j is actually -j. Again, there's a previous presentation that looks at the powers of j if you want to refer to that for reference. So tidying up on the next line, I get cos cube theta plus j3 cos squared theta multiplied by sine theta minus, don't forget the positive and the negative here makes the negative term here, so that's why I'm taking away. 3 multiplied by cos theta multiplied by sine squared theta, and then minus j sine cubed theta. Now because we're only equating the real parts in this expression, then my cos 3 theta on the left hand side from the previous slide is equated now to the cos cubed theta minus the 3 cos theta sine squared theta. Those are the only real parts above. So just to reinforce that, the only real parts I have in this line is this term. This is the complex part because it's associated with j. This is a real part. Notice it's negative though. Take the negative sign with you. And the last term is a complex part because that's associated with j. So the only real parts I have are cos cubed theta minus 3 cos theta sine squared theta. So there's my trigonometric identity for cos 3 theta using the above process. If I want to just check it numerically, I'm going to let, for example, theta equals 60 degrees, an arbitrary value I've just chosen for convenience. And if you put theta is 60 degrees in the left hand side and evaluate that, you find that's -1. And if you put theta in the right hand side expansion and evaluate that, you find that's -1 also. So the identity checks out. Example 1a continue, we're now looking at part B. We're now asked to find the trigonometric identity sine theta multiplied by cos 3 theta. So in 4, we're going to use the result from part A of this example to help us generate the identity sine theta cos 3 theta. So we've got sine theta on the left hand side multiplied by cos 3 theta. So on the right hand side I've got my sine theta, but I'm replacing the cos 3 theta on the left hand side with the previous result from part A, which is cos cubed theta minus 3 cos theta sine squared theta. So that's from the previous slide. The hint in the question is to use the trig identity sine squared theta is equal to 1 minus cos squared theta. That's a standard trigonometric identity, often called a Pythagorean trigonometric identity, which we're using here. So what we're going to do is replace the sine squared theta term in this equation with the 1 minus cos squared theta term in this equation. So on the next line I've expanded the 1 minus cos squared theta in the brackets with the -3 cos theta term. So now I get cos cubed theta minus 3 cos theta plus 3 cos cubed theta in the bracket, and it's all multiplied by the sine theta outside the bracket. Just be careful of the change of sign that occurs because of the -3 here and the negative cos squared theta here ends up with a +3 cos cubed theta. So finally, simplifying inside the bracket, I've got a cos cubed theta here, and I'm adding that with a 3 cos cubed theta here. So that makes 4 cos cubed theta minus 3 cos theta in the bracket, all multiplied by sine of theta. So we now have a trigonometric identity for sine theta multiplied by cos 3 theta. Again, we can undertake a numerical check if we want to. If we let theta equal, say, 60 degrees, then put in 60 degrees on the left hand side and evaluating, we have a value of -0.866. And put in 60 degrees into the right hand side of the identity and evaluating, we again find we get -0.866. So checks. Example 2a. In part A, we're asked to write sine 4 theta in terms of cos theta sine theta by applying deMoivre's theorem. In part B, using the result from part A and an appropriate Pythagorean trig identity that we must choose, we've got to determine the trigonometric identity for sine 4 theta multiplied by cos theta as a function of sine theta only in this case. So again, we're going to start from deMoivre's theorem as we did in example 1a, stating that here. Part A. So from the question, we've got to prove an identity for sine 4 theta. We need to note that in this case, n is equal to 4 and r will be equal to 1 again, as in example 1a. So step 1, just rewriting the above equation, putting deMoivre's theorem on the left-hand side. we notice that the r is equal to 1 again, so 1 to the 4 is 1, and the n is 4, so we just replace the n's with 4 on the left hand side, and on the right hand side we've got the power of 4 here, 1 for the r. So on the left hand side it simplifies to cos 4 theta plus j sine 4 theta, and on the right hand side it simplifies to cos theta plus j sine theta all raised to the power of 4. As with the previous example, we need to decide whether we're going to compare real parts or imaginary parts. Now in this case the sine 4 theta is associated with the j term, as we can see here, so we're only going to equate then the imaginary parts in this particular question. So on the left hand side we get the j sine 4 theta. We're going to have to expand the right hand side of the identity, the cos theta plus j sine theta to the power of 4, we'll look at on the next slide using Pascal's triangle. So example 2a continued. Don't forget we're trying to expand now cos theta plus j sine theta all to the power of 4. So step 3, we're going to expand the right hand side of the previous equation using Pascal's triangle, generically the a plus x to the power of 4, which is this line of table 1, repeated here for convenience. So looking at the pattern here, from the expansion of a plus x to the power of 4, we have 1 a to the power of 4 plus 4a cubed x plus 6a squared x squared plus 4a x cubed plus 1 x to the power of 4. So in this case the a is equal to cos theta and the x is equal to the sine theta. So following the pattern through for the a plus x to the power of 4, our a will be cos theta to the power of 4, plus it will be 4 multiplied by the a to the power of 3 x term, so that's cos cube theta in this case, multiplied by the j sine theta. So the third term is plus 6 cos squared theta multiplied by the j sine theta all squared. The fourth term in the series is 4 cos theta multiplied by the j sine theta all cubed, and then the final term, the fifth term, is plus j sine theta all to the power of 4. So don't forget a plus x to the power of 4 has 5 terms in the series. So be careful on the next line, looking for the higher powers of j. We'll get a j squared here. When we square j sine theta, we get j squared sine squared theta. Here we've got a j cubed term because we've got a j sine theta all cubed, so we get j cubed sine cubed theta. And looking at the final term here, we get j to the power of 4 sine to the 4th theta from the above line. On the next line, noting that j squared is negative 1, noting that j cubed is negative j, and noting that j to the 4 is 1. So be careful there, that's using the powers of j, and again we've looked at that in the previous presentation if you want to go and review that for background reference. So simplifying on the next line, we get cos to the power of 4 theta plus j4 cos to the power of 3 theta multiplied by sine theta minus 6 multiplied by the cos squared theta multiplied by the sine squared theta minus j4 cos theta multiplied by the sine cubed theta plus the sine to the power of 4 theta. So now, as mentioned on the previous slide, we're only going to equate the imaginary parts, because on the left hand side we have j sine 4 theta on the previous slide, so on the right hand side we're only looking for the imaginary j terms. So reviewing the right hand side of the identity, we have an imaginary term here and an imaginary term here. Notice this one is negative. So on the next line we get j4 cos cube theta sine theta minus j4 cos theta sine cube theta. Factoring on the j4 on the right hand side, we get j4 and in brackets cos cube theta sine theta minus cos theta sine cube theta. On the final line I've written the sine 4 theta without the j, so sine 4 theta on the left hand side is equal to 4 and in brackets cos cube theta sine theta minus cos theta sine cube theta. So there's our trig identity for sine 4 theta. Example 2a continued. Now looking at part B. We're asked to find identity sine 4 theta multiplied by cos theta. So in step 4 we're going to make use of the solution from part A. So now on the left hand side of our identity we've got sine 4 theta cos theta, what we're trying to find, and on the right hand side what I've done is incorporate the solution from part A of example 2A. So sine 4 theta on the left hand side actually equates on the right hand side to the 4, and in brackets, cos cube theta sine theta minus cos theta sine cube theta, and that's solution for part A of this example. I've written the cos theta term the same on both sides of the identity. On the next line what I'm doing is expanding the bracket by cos theta on the right hand side, so cos theta multiplied by the cos cube theta sine theta, and then cos theta multiplied by the negative cos theta sine cube theta term. So that simplifies on the next line to 4 outside the bracket, cos to the power 4 theta multiplied by sine theta minus cos squared theta sine cube theta. Now in the question we're asked to choose an appropriate trigonometric identity to help us arrive at a solution for sine 4 theta cos theta in only sine theta terms. So in this case in step 5 I'm going to use a trig identity. Cos squared theta is equal to 1 minus the sine squared theta. In other words, I'm using the Pythagorean trigonometric identity we've seen in previous presentations. So what I'm going to do in this line is replace the cos to the power 4 theta and the cos squared theta terms with the 1 minus sine squared theta. Now be very careful here. When I replace the cos to the power 4 theta term, in other words this term here, with the 1 minus sine squared theta, I will need to square it. So this is replacing the cos squared theta term, but I will need to square that to get a cos to the power 4 theta term. So think that through very carefully for yourself there. We've got to make cos to the power 4 theta. We know that 1 minus sine squared theta is cos squared theta. So if we square a cos squared theta, we will get a cos to the power 4 theta term. So in other words, we have to square the 1 minus sine squared theta term. And that's what's been done here. So again, just be very careful with that. Think that through for yourself. This cos squared theta term here is simply going to be replaced with the 1 minus sine squared theta. So on the next line what I'm doing here is expanding the 1 minus sine squared theta squared term to get my 1 minus sine squared theta multiplied by 1 minus sine squared theta expression. And here I've just expanded the bracket with the sine cube theta term. So I end up with 1 multiplied by sine cube theta, so that's sine cube theta. And I've got a negative sine squared theta multiplied by sine to the power 3 theta. So that's a negative sine to the power 5 theta. So again, just be careful there with your expansions and your directed signs. On the next line, I've expanded the binomial brackets of 1 minus sine squared theta to end up with 1 minus 2 sine squared theta plus sine to the power 4 theta. Of course, that's still multiplied by the sine theta term there. I just repeated this as in the previous line. And on the next line, I'm multiplying this bracket here by the sine theta term to give me this expression here. And here I'm just counting for the negative outside of the bracket when I write down this expression here. So again, be very careful there for directed signs. So simplifying on the last line, I get in brackets the sine theta term from the previous line, and be careful, I've got a negative 2 sine cube theta there and a negative sine cube theta term there. So that gives me negative 3 sine cube theta. Again, be careful, I've got a plus sine to the power of 5 theta term there and a plus sine to the power of 5 theta term there. So that will give me plus 2 sine to the power of 5 theta. So now I have my trigonometric identity for sine 4 theta multiplied by cos theta. It now equates to 4 open bracket sine theta minus 3 sine cube theta plus 2 sine to the power of 5 theta. So my identity is in terms of sine theta terms only, which was the requirement in the question. If you want to undertake a numerical check, then let's let theta say, for example, 30 degrees in this case. So I simply put the 30 degrees for theta on the left hand side and evaluate the expression. That comes to 0.75, and I put theta in the appropriate places on the right hand side of the identity, and again that evaluates to 0.75. So the identity checks out. Tutorial exercises. Exercise 1A and part A. We're asked to write cos 4 theta in terms of cos theta sine theta by applying deMoivre's theorem, and in part B, using the result from part A and an appropriate Pythagorean trig identity, we're asked to determine the identity cos 4 theta sine theta as a function of sine theta only. The answers are given here in the square brackets. Exercise 2A. In part A, we're asked to use deMoivre's theorem to prove the validity of the trigonometric identity. So we're given this identity here. So sine 5 theta is equivalent to 5 multiplied by the sine theta minus the 20 sine cube theta plus 16 sine to the power 5 theta. So basically in this question they've given us the answer of part A. We have to prove it using the process from the previous examples. So part B requires us to use the proof from part A, and assuming an appropriate trigonometric identity, we've got to prove that the sine of 5 theta multiplied by cos squared theta is equal to this expression shown here on the right hand side. Part C, further using part A solution, we've got to show that sine 5 theta cos to the power 4 theta is equal to this expression on the right hand side. Part C is similar to part B in its approach, it's just that you've got the cos to the power 4 theta factor as opposed to the cos squared theta factor, so be careful when you expand the terms on the right hand side that you account for those higher powers. Similar approach as used in example 2A. Exercise 3A, part A, we're asked to use deMoivre's theorem to prove this expression for cos 6 theta. Let you look at that. And then part B wants us to use the answer from part A and an appropriate trig identity to show that the expression for cos 6 theta multiplied by sine squared theta is shown on the right hand side here. I'll leave that with you. Here's the bibliography used to help generate this presentation. I would encourage you to review these reference sources, very good reference sources again on this topic area. I do hope this has been of use to you, and thank you for viewing.